We're on to question 27. Fission and fusion are two distinct types of nuclear reaction. Fusion can be described as a process in which, all right, so you just want to know the difference between fission and fusion. And fission happens with big atoms when they split into smaller atoms to become more stable. And fusion happens when two small atoms fuse together to become a larger atom. But the important thing is that fission is for big atoms, fusion is for small atoms. So which one of these correct is most correct for fusion? Right here, too low mass nuclei combine to form a new nucleus with an atomic number less than 60. 29, how many neutrons are liberated in the following reaction? So it's balancing. On the left side, you have 94. And so on the right side here, you have 94 also. So then you got 94 right there, so this must be a 0. And this number here, well, we're talking about neutrons here, right? So we know that must be 1. We just need to know how many of these, what number am I going to put here so that this balances out. And what number is that going to be? Well, this and this add up to 230. Well, I can't see that number. 37 and 99, so 236. And this number add up to 240. So it must be 4 neutrons. All right. Number 30. Number 30 says, how much energy is released in the fission reaction of uranium to produce krypton and barium as described below? So here we go. This is your classic fission reaction. You have uranium-235. You add a neutron to it. It becomes uranium-236, gets very unstable, and then splits into these two and also releases 3 neutrons. So if you're going to use the numbers from the textbook, then the atomic mass in atomic mass units of a neutron is 1.008665. So what we have to do here, and this is very tedious because of all these huge numbers, we've got 1 neutron there, which is 1.008665. And we're going to add it to the uranium-235 right here, and that will give us the mass of our products. Okay, and then we're going to get a number, which is the mass of our products. Actually, we'll go through it. 236.052.595. Incidentally, the solution that I have on D2L, I use the slightly different mass for neutrons, so I get a slightly different answer. But if you use the one in textbook, you get the exact answer. So let's just go with that one. So that's what you get for the mass of your reactants. Did I say products? If I did, I meant reactants. Those are your reactants. And then if we add these, you get the mass of the products. So it will be this plus 3 times the neutron, 3 times that value there. And that turns out to be 235.866563. So the mass of your products is slightly less than the mass of your reactants. To get the energy that's released, we're going to just subtract those 2 numbers. So subtract those numbers, and that's going to be your mass defect. So when you subtract those, you get And remember, that's in atomic mass units. That's your mass defect in atomic mass units. You then have to convert that to kilograms, because what we want to do here to get the energy is we just want to use E equals mc squared. But you need the mass in kilograms. So to get that into kilograms, you got to multiply it by the number that's on the back of your formula sheet. I think actually on your formula sheet is just 1.66, but if you multiply it by that number, 1.660539 times 10 to the negative 27 kilograms, you'll get the answer in kilograms. And then whatever that answer is there, plug it in right there, multiply by the speed of light, square it, and you're going to get your answer in joules. Did I do that? Okay, yeah, so this turns out to be 3.0. This gives you an answer of 2.78. I'm starting to lose all the significant digits. Times 10 to the negative 11 joules. So that's your energy release in joules. To get it into electron volts, divide by 1.6 times 10. And it's going to give you that. Well, it's going to give you 173763782, which is 174 mega electron volts. Okay. Moving on to the numerical response. An oxide ion with this mass enters a magnetic field is perpendicular to the direction of travel. The radius of curvature is 4.5. The speed of the ion is. All right, does sound familiar? We got a charged particle moving in a magnetic field. The centripetal force must equal the magnetic force. And in this case, we're solving for V. That cancels out that. So V equals QB, move the R there, divided by M. And that's a straightforward question. You've got Q. Well, actually, let's do it. Q is 3.2. Why is it 3.2? Because it's an oxide ion, has 2 excess electrons. So the elementary charge times 2 times the magnetic field strength. Don't forget to put it's milliteslas, so you got to put times 10 to the negative 3. Radius. Change the centimeters to meters, and you're going to get an answer of 3,600. Meters per second, but they want the answer in kilometers per second, so move the decimal place 3.6 kilometers per second. Number 32, we've got a Millikan oil drop. Question, the oil drop has a charge of 5e, which means it has 5 excess electrons, and if it has 5 excess electrons, and each of those electrons has this charge, then the charge, the overall charge Q equals 8.0 times 10 to the negative 19 coulombs. Falls between 2 horizontal plates that are 2 centimeters apart. Okay, so this is a little different because it gives us the distance between the plates. The oil drop is suspended. So if it's suspended, when that voltage is applied, 300 volts, the mass of the oil drop, if suspended, that means the gravitational force must equal the electrostatic force. mg equals EQ. The only thing that's different about this question is they don't give you E, but they do give you D and V, and therefore you can calculate E, or if you want, you can just substitute it into that equation. So let's do it. Let's do it that way. So M is going to end up equaling VQ D over DG, right? Because sorry, got something in my throat. Okay, so now we have the voltage, we have the charge, we have the distance between the plates, and we have gravity. Plug the numbers in, and you are going to get 1.22 times 10 to the negative 50. 1, 2, what is it, 1 N and 1 C and B, C, D. And that's how you would fill that one in. How are we doing for time? How many more do we have? Well, you know what? We'll do the remainder of the questions in the next video.